afternoon, everyone. Welcome to the Boltzmann Session series presented by Horizon IIT Madras. Today we have with us Ms. Prachi Prajapati from PRL Ahmedabad. Prachi started her research career at IIST and has since been working on Wolf-Rayet stars and their dynamics at the Physical Research Laboratory in Ahmedabad. It's great to have you with us, Prachi. Over to you now.
Hello everyone. Thank you the organizers for arranging this Boltzmann lecture series. And myself is Prachi and I'm working at PRL currently. So today I'll be talking about this particle acceleration in Wolf-Rayet stars. Start first with explaining what are the Wolf-Rayet stars, and then we can go to particle acceleration and how Wolf-Rayet stars contribute to this. So, as we all know that our ancestors unofficially started astronomy looking at the stars in the night sky, finding crazy shapes, which we today know as constellations, and then eventually the small telescopes the observations began with small telescopes where people started studying stars in detail. And in general, like if you ask some even school-going kid, then what is astronomy? Then he will most probably answer that it's something related to looking at the stars in the night sky. So let's understand that how the stars are formed. So the birthplaces of stars are mostly these giant molecular clouds which have gas and dust in them. So in this picture is an artist's impression showing this scenario that how the stars are formed. So from these clouds at various places, the clumps starts forming initially. So therefore the density increases locally at the place where this clump is forming. This leads to the gravitational force to increase in the clumps, and further it accretes matter to form denser cores, which we can see here. So these dense cores are actually the precursors of stars, and eventually it leads to the formation of a young star, where in the young star, initially we expect the nuclear reaction to start. So at that point, we can tell that the star is born, and it is also known as zero-age main sequence star. So the age is 0 for the star because it's just born. So now the stars actually evolve in two different ways based on their mass, which it has when it is reaching the zero-age main sequence. So after the birth, this further evolution is quite dependent on the initial mass, and the low mass stars like our sun, which are having the mass of the order of 1 solar mass, they evolve in quite peaceful manner as shown in the top panel here. So after the main sequence, it evolves to the red giant phase, and then it dies as a white dwarf, going through the exotic phases like planetary nebula. But this is a very peaceful manner, and they don't show much of exotic phenomenon, which are very powerful as compared to the supernovae-like phenomenon. So these stars are called low mass stars, whereas we also have massive stars, which starting from the zero-age main sequence, they evolve to the red supergiant phase, where the radius is much larger than the red giant phase. And they die in very exotic manner. Very powerful supernovae explosions can be expected at the end of the massive star's life, which leaves either neutron star or black hole as the compact object as a remnant. So in particular, these massive stars are defined as the stars which are having the mass, initial mass, as greater than 10 solar masses, and within them, the stars which are even above 40 solar masses, they have a Wolf-Rayet phase. It's an evolutionary phase which they go through in between these two phases, red supergiant and supernova explosion. So we can understand that the Wolf-Rayet phase is the phase just before the death of the massive star. So now I will be talking about that in upcoming slides. But before that, let's just have a comparison of what kind of lifetime we expect for stars of different masses. So first of all, if we see the sun-like stars, which is one solar mass stars, so they do live for a longer period, like roughly 10 billion years. But if you eventually go to the higher mass stars, so about 10 solar mass, the massive stars are there. So they live only for a few million years. So if you compare these low mass stars with the high mass stars, then the lifetime of massive stars is very less. So now let's understand like what are the basic properties of massive stars. So living in a solar system, we know that the sun is our parent star and planets are kind of nothing in front of sun if we compare the sizes or mass, etc. But then sun itself might be thinking that there might be even more massive stars and they do exist. So these massive stars generally are, as I told, they are having mass of more than 10 solar masses, which is quite massive. And they are also very hot. So their surface temperatures are much more than solar surface temperatures. As well as one of the very important feature of massive stars is that they have a very strong stellar winds from emitting from their surfaces, and it also causes exotic mass loss from their outer layers. So in short, these stars are kind of monsters if we compare them with the low mass stars. And so these massive stars, due to their all this exotic properties, they also give kind of very strong input to the surrounding interstellar medium, which is surrounding ISM. So it can be like described in three ways. So since they are having very high temperature on the surface and very strong stellar winds, they lead to radiative and mechanical input to the surrounding medium, as well as they are also enriching the surrounding medium chemically. So in astronomy, we generally call hydrogen and helium as the primary elements, and then all other elements except these two are called metals. So massive stars are one of the major contributors to increase the metallicity in the surrounding interstellar medium. So I will discuss about this chemical output in the coming slides. So before that, so let's come to the Wolf-Rayet stars. So the name itself has this word called wolf, but it doesn't have anything to do with the wolf, which you might be thinking. It's basically these two people, like they were astronomers, and they accidentally found these stars which were having little different features than other stars at that time. So this is Wolf and Rayet. So these two astronomers have discovered this stars called Wolf-Rayet. So that's why the name goes on their names. So yeah, so like the main properties, as I told, since they are the evolved phases of massive stars, so obviously at the main sequence they will be very massive and very hot. And to understand this evolution of stars in astronomy, we generally plot this kind of diagram where on y-axis we keep luminosity of the star versus on x-axis we have temperature of the star. So this is the surface temperature, which we also call as effective temperature. So this figure is called HR diagram, which is Hertzsprung-Russell diagram. So here you can see this diagonal patch, which is called the main sequence, where any star, which is a newborn star, it steps into this main sequence first, and then as it evolves, it either goes to giant phase for the low mass part, and the massive stars evolve to the supergiant phase, and which I described earlier in the figure. So in particular, if you see these part, so these are low mass stars. As we go upwards, here are the massive stars. Also, their lifetime is written in the green color here. So if you go towards very massive end, like more than 40-45 solar mass, so there you can see this WR. So because these stars, the another version of these part is shown here. So the stars which are more than 40 solar mass, so if you see the evolutionary path of these stars, so they go through this Wolf-Rayet phase during their life, and the luminosity is tremendously high. Even the temperature is quite high. This is in the log scale. So we can see that these stars during their Wolf-Rayet phase are kind of very hot and quite luminous. So let's go to some features like observationally how these stars were discovered and what are the properties of these stars. So the discovery of these stars were actually made based on the observed emission lines from the ionized gas on top of the black body spectrum. So generally we know that star is kind of we can assume it as a black body. They generally, like sun-like stars, generally don't have emission lines, but these kind of stars, since they are very hot, they can ionize the material in the top layers, near to the top layer, and that causes the production of emission lines. So and that is how they were discovered. So they have these emission lines in their spectra, and since they are evolved phases of massive stars, so evolved as in they have already passed these main sequence phase and then they are evolving. So main sequence is the phase where hydrogen burning happens. So that is why, since they are already like they already crossed main sequence, so hydrogen will be obviously depleted, or there will be very less hydrogen. And subsequently, they also show higher elements like carbon, nitrogen, and oxygen. Because if you want to understand this in a very nice manner, so this is called onion shell structure model of star. So you have a hydrogen layer first. So when the shell burning happens, firstly this hydrogen gets fused to helium. Then eventually helium, carbon, oxygen, neon, all this fusion happens until it reaches the iron core, where the supernova explosion is like it happens that it ends their life as supernova. So these stars, like even first, it goes a step by step. So after hydrogen, they fuse helium. So some Wolf-Rayet stars do show helium emission lines, but most of them are mainly showing the nitrogen, carbon, and oxygen emission lines. And based on that, they are categorized in subclasses as WN, WC, and WO. So WN means it is showing the nitrogen enrichment on their surface. So that means this phase is going on when nitrogen is getting fused. Then eventually carbon and oxygen. So as it goes towards WO, it becomes hotter and hotter. So that is how the evolution happens. And within these three subclasses as well, they have even more categorization as 0 to 9. So that is not important as of now, but I will talk about it when at the point when it comes. So since the stars are very rapidly evolving, so we expect less population of these stars to be observationally to be present for us to observe. So in our own Milky Way, there are only around 1,000 Wolf-Rayet stars present, and there are a few of them which are present in LMC and SMC. So apart from this, the luminosity, the mass loss rates, and wind speeds and temperatures, if you see these numbers, so for example, to get an idea of how exotic these numbers are, you can compare it with the numbers for the sun, like our own sun, so which is a low mass stars. So the luminosity of the sun is 1 solar luminosity, where this is kind of 10 power 5 to 10 power 6 times of solar luminosity. Mass loss rates for the sun are roughly 10 power minus 14 solar mass per year. These are quite higher than that. And wind speeds for sun, if you see, then it is around 400 to 500 kilometers per second, whereas Wolf-Rayet stars possess wind speeds which are quite high, like thousands of kilometers per second. and the surface temperature of Sun is around 6,000 Kelvin, where these massive stars and their evolved phases are having surface temperatures of starting from 50,000 to 100,000 kelvins. So this gives an idea that how hot and the monster-like feature which I mentioned earlier. So how that comes in. So now the second part in my title of the talk was particle acceleration. So we'll come to the relation of this particle acceleration and Wolf-Rayet stars at the end of the talk. Before that, let's just go through very briefly like what is the particle acceleration and how massive stars contribute to this. So in recent years, people have started looking at the aspect where massive stars are investigated as sources of particle acceleration. And this is done through the detection of non-thermal emission, which I'll be talking about in the next slide. So where we detect non-thermal emission, which tells us that there is a presence of accelerated particles which are having relativistic speeds. So some of you might have studied diffusive shock acceleration, which is a Fermi first order mechanism to accelerate particles in physics courses. So in astronomy, if we see, then like generally DSA mechanism needs presence of supersonic outflows or supersonic motion to create shocks. And in astronomical objects, if we see, then supernovae remnants or big hera objects or jets, these are the places where you do expect presence of shocks being present. So to understand DSA, it's not really difficult, but it's quite intuitive and tricky. So let me just briefly explain the overall scenario. So here in figure A, we can see that there is this shock front present, which is a hydrodynamical shock. So you have local magnetic fields present everywhere in the galaxy, in our own galaxy or even in the universe. So we do have some kind of local magnetic field present, and there is the shock front. So now there are particles which are in the upstream and downstream. So okay, first downstream is the region where the shock front has already passed, whereas upstream is the region where the shock front is not yet come, because this kind of unaffected region from the shock front moving. So there are these particles in upstream which can cross the shock front and try to go to downstream, whereas there might be some particles in downstream which also can try to go to upstream. So when we have this magnetic field present, so it acts as kind of a mirror, where if particle tries to cross this and come here, so it experiences an head-on collision or kind of head-on interaction with this material here, and it tries to go back to downstream. So this kind of multiple trips of particle moving from upstream to downstream and downstream to upstream, it kind of creates increase in the energy of the particle which it initially possessed. So this continues till the particle leaves this whole system, and at the end of these all, let's say k trips are happening to and fro, so the particle's energy will increase by that factor. And theoretically, if you calculate everything, then this comes out to be that change in energy of the particle will go as the velocity to the power 1, where velocity is basically the velocity of the shock front. So that is why it's called Fermi first order mechanism. And this kind of accelerated particles are injected in the surrounding medium, and it follows the power law with the power law index P, where N is the number of particles with energy E, and it goes as e power minus p, so it is a negative power law. So now, having said that, DSA is understood that like presence of shock is required to accelerate particles, and observationally, the presence of such accelerated relativistic particles is detected via non-thermal emission, as I told earlier. So let me just briefly tell like what is the difference between thermal and non-thermal emission. So first of all, I'll talk about thermal free emission. So why it's called free is because these kind of emission is generally seen in the medium where ionized gas is existing. So we know that in ionized phase we have electrons and some kind of ions. So when an electron is trying to let's say it's moving at velocity v1. When it reaches near to the ion, its path gets deflected, the direction changes, and it attains different velocities. So since the direction has changed, it's getting accelerated here. So this change in energy can be it gets compensated by the emission equivalent to that delta E. So that is how this emission which is getting emitted, that is called thermal emission. So if we like the theoretical calculations, if we do, then we get the spectra. Spectra is basically the flux density versus frequency. So this is the typical spectra for thermal emission, where if we see tau is the optical depth. So if we go towards higher frequency, it is optically thin medium. So there we expect the power law, which is called spectral index. So this power law index is different from this. This is for Ne versus E, and this is for flux density versus frequency. So this alpha is the power law index, which is called spectral index generally. So we expect minus 0.1 to be the spectral index for thermal emission. Whereas this case, which I discussed here, it's for ionized medium. Homogeneous, that was the assumption. So homogeneous means that the number density of electrons and ions are same at all different places in this system. Where now when we come to the case of stellar winds, which is our main goal to study the massive stellar winds. So in this case, that assumption which was there, that homogeneous number density is present, that doesn't hold true. So here, as we go radially outwards from the star, so we expect the number density to decrease with the negative power law. So generally it's taken as inverse square law. So NR goes as R power minus 2. And if we do the same calculation, which we do for ionized medium, then we can get the spectral indexes plus 0.6 for stellar wind scales. So this was the thermal emission. And now let's come to the non-thermal emission, which we actually try to understand in order to understand the particle acceleration. So let's say if we have a local magnetic field present and some charged particle is gyrating around these field lines, then its motion is such that since it's gyrating, the velocity direction is getting changed each moment. That's why it's getting accelerated as it moves forward. So due to this, it creates emission, and this emission is actually seen only when the electron or the charged particle its velocity is kind of pointed towards you, the observer. So that is due to the relativistic beaming effect, which I won't go into detail of it. So just if someone wants to know, then they can just ask in the question probably the more details about it. So this emission is called non-thermal synchrotron emission. It's kind of we can give the analogy that it's kind of relativistic cyclotron, And for this kind of emission, if we mathematically solve the emission model, then we can get the spectra, which is this for one electron, one particular charged particle. So it has this kind of emission spectra, and it's not that in the medium only one electron might be present. There might be a bunch of electrons. So if we combine for all electrons with different velocities, then we get this kind of combined spectra. So that gives this negative power law, which is like the flux density is proportional to frequency to the power spectral index, which is alpha. And this alpha here is negative because, as we can see here, it's going downwards in the log plot. So this alpha is in fact related to the power law index P, which we have seen in the DSA mechanism, the particle acceleration mechanism. So value of alpha is in fact minus P minus 1 by 2. So now coming to the observational part, so where the detection of the non-thermal emission in massive stellar systems generally is seen to be correlated with binarity of the system. So we know that like the stars are mostly formed from this molecular clouds where number of clumps were there. So generally, if we see observationally, then most of these stars are found in binary systems rather than being isolated, specifically massive stars. So in case of binary systems with two massive stars, so let's say we have this one OB type star here or Wolf-Rayet star here and the second massive star here. So both of them, since they are very massive, they have very strong stellar winds, and when they are orbiting around the common center of mass, when they come close, these winds can interact with each other to form a shock front here. So the material ejected due to their mass loss can get shocked where the place where the shock is present. And at this place, we do expect the presence of shock front, and which can lead to particle acceleration, leading to emission of non-thermal emission. So observationally, if we confirm that synchrotron is present in this region, then it can intuitively tell us that yes, the particles are getting accelerated at this place. So this is the scenario where massive stars are in a binary system, where in addition to this scenario, even if we see stellar bow shocks, these are kind of bow shocks, as in it has a bow-shaped shock front, and these are like generally seen in the cases where the massive star is a runaway massive star. So in the this will be very intuitive in this figure. So let's say this star is moving in this direction, and there is this surrounding medium here. So due to this motion, it pushes the material towards this direction, and it causes the formation of the shock here, which is in the bow-shaped like feature. So these three scenarios are like during the whole life of massive stars, we expect them to accelerate particles in these three different scenarios as of known today. So first is the particle accelerating colliding with binaries, which I talked about, which is a binary system case. And other is the bow-shocked region, where the runaway star can cause particle acceleration. So the third one is very well known and well studied, which is the supernova remnant. So at the end of the star's life, it explodes as supernova, and the remnant, which is like the material which is getting ejected outwards, it can cause particle acceleration due to interaction with the surrounding medium. So these three are the scenarios in which massive stars are known to contribute as the sources of cosmic rays. But there is to generalize this idea, this is not a full thing. Like there's something still missing, which is the role of the isolated massive stars. So we have already discussed binary system of massive stars and supernovae and everything. But how during the life of the isolated massive star it contributes to particle acceleration, that is observationally not yet well understood, and that is like dependent on observational constraints as well, because if we see massive stars, then like based on their initial properties itself, they are very rare compared to the sun-like stars, and they evolve very rapidly, and therefore it's difficult to get good senses of like massive stars to study. And even in the massive stars, the isolated nature itself is a rare nature because most of them are found in binary systems. So there are a very few single isolated stars which are massive and which goes to Wolf-Rayet phase during their life cycle. So these kind of stars, let's concentrate on the isolated stars now. So when the star is isolated, surrounded by the interstellar medium, then since it's massive star, obviously I extensively told earlier that they have very powerful stellar winds. So the interaction of these stellar winds with the surrounding material, it leads to the formation of nebulosity around such stars. So these are some pictures of they are called stellar bubbles or Wolf-Rayet bubbles in case of Wolf-Rayet stars. So these are the pictures which are having the nebulosity around the central massive star due to the interaction of their winds with the surrounding medium. And generally, like this kind of bubbles are expected to be in quite spherical shape, but it's not always true. Due to many factors like density, inhomogeneity in the surrounding, etc., it also can have a very exotic and very complex these shapes. So there are some crazy shapes as well, as you can see here. This WR7, it has a bubble which kind of relates to the shape of Thor's helmet, and it is in fact it is known as Thor's helmet as well. If you can Google, if you want to Google, you can just see that. So yeah, this kind of it's very interesting to see these kind of bubbles around the massive stars. And now theoretically, if we see that why we are looking for particle acceleration in isolated stars, so theoretically, if we can confirm that yes, they can accelerate particles, then we can propose for observations further. So if we see this figure, which is a general figure with two massive stars. So first scenario is due to the wind collision, which I have already explained. But the other two, B and C, these two are the scenarios which might lead to shock formation in case of isolated stars. So assume that this star B, this star here, it's isolated and this star is not present as of now. So one scenario could be that the shock can get formed in this co-rotating interaction regions within the stellar bubble itself, which is shown here. And another scenario could be that the stellar winds of these isolated massive stars, it can interact with this interstellar medium surrounding it to form the shocks, which is shown here. So theoretically, yes, we can expect that the shock formation is possible for even isolated massive star, which can lead to production of non-thermal emission as well as particle acceleration. So to observe this, since I told that it's very rare to find isolated massive stars due to many constraints, in our own galaxy there are only four of such WO2 type spectral type stars, and one of them is this WR102. So WO, as I have told earlier, it's oxygen-rich Wolf-Rayet star, and this 2 index is, as I told that time, that they have subclasses starting from 1 to 9. So this is 2 from that subclass. So if we have the subclass which is near to 1, that would be having more surface temperature in comparison to the one which is towards 8 or 9. So yeah, this WO-102 is one of those very interesting sources, and it also it also has this a bubble around it. It's named as G2.4 plus 1.4. So this WO-102 is an isolated single star, and it is oxygen rich, and it is present at around 3 kiloparsecs from us, and it has surface temperature of roughly 200,000 Kelvin. So this is one of the hottest star known today, and its stellar winds are quite supersonic. So their speeds are around 5,000 to 6,000 kilometers per second, and the image of this bubble, it's the same bubble which I have shown here. So the orientation is changed a little bit. So yeah, this is an optical image of this bubble, and this is an infrared image. So you can see that the shape is not spherical for this particular nebulosity. Rather, we can see there are some interesting and complex filamentary structures, like multiple rings and loop-like structures are present. So therefore, this is one of the most interesting sources, and since WO-102 is an isolated star, so we can expect the particles to get accelerated within this bubble. And for this purpose, the observations were planned, and observations what kind of frequency we should plan for, that depends on the theory which I discussed earlier. So in the case of stellar winds around massive stars, we have two kind of emissions. One is thermal and other is non-thermal synchrotron. So since the thermal emission was having positive power law with 0.6, it goes as this blue line as shown here. Whereas the synchrotron emission, which is non-thermal, it was having a negative alpha, so it is shown here as this green line. And this alpha value, as I told, it's minus P minus 1 by 2, where P is the same P which I discussed in the Fermi first order mechanism. So if this figure tells us that if we go towards the lower frequencies and hence the higher wavelengths, the dominance of synchrotron emission is more over the thermal emission. So therefore, it's better if we go towards the higher wavelengths, like radio bands. So that's why we have planned the radio observations for this particular source. And for that, we used upgraded giant radio telescope, which is a facility by NCR TIFR at Pune. So I won't go into the much technical details of the observations and data reduction, but what observations we have done is we have observed the source at different frequencies, like 2 frequency bands, and we have done the data reduction to get these images. So these are called radio maps at different frequencies, and these maps are created. So we can see that, and the morphology of the bubble is as we have seen in the optical and infrared images as well. So it has this interesting filamentary structures present, and we can, based on these maps, we can always try to get the flux values for this bubble and plot it with respect to the observed frequency. So that leads to this plot, which is called spectrum. And for this particular spectrum, if we fit a straight line, then we can get the value of spectral indexes minus 0.83. So since the value of alpha is negative, we can confirm that this bubble has non-thermal emission present in that. And to understand the presence of particle acceleration, or like creation of relativistic particles from this non-thermal emission, we can model this thing, like model the emission from whatever we have observed. So this modeling leads to the outputs of the model will be local magnetic field, which is kind of contributing to this particle acceleration, and it also gives us an idea of the efficiency of particle acceleration. So these two are the values which we found from our model, and this is the modeled spectra which is shown here. So this gray line is the model, and these black dots are the observed data points which are overplotted on the model. So to get the intuition from what kind of numbers we are talking here and how it is compared with the other sources of galactic cosmic rays, let's compare this number with the from supernovae. So let's say this is very well known, like supernovae are one of the major sources for production of galactic cosmic rays. And this paper, Duffy and Drury, they talk about the numbers of the efficiency of accelerating the particles from supernovae. It's roughly 10%. And what we found for isolated stellar bubble is it came out to be 0.6 to 17%. So this tells us that it's quite evident that even the isolated massive stars are able to generate the accelerated particles, which are basically the galactic cosmic rays, where you have the input, everything, whatever is coming as mechanical power from stellar winds of the central massive star, that is the input to the surrounding medium, which can create shocks and leads to particle acceleration to generate galactic cosmic rays. So this study confirms that even since the isolated massive stars are also kind of one of the sources to generate galactic cosmic rays, the full picture is kind of completed now. But since this is only one observational study, it's always good to have more and more observations. But since these stars are rare, it's difficult to do, but it's always like the work is always should be in progress to have more observations for such kind of stars. Summarizing the talk is that first I talked about the massive stars and their exotic life cycle. Generally, it's compared like the analogy of poor people and rich people. So massive stars are one of the richest people who has very hot temperature and strong stellar winds and everything, but then they live for a very short time, and whereas the poor stars like sun-like stars, which are low mass stars, so they evolve quite peacefully and live for a longer period. So yeah, after that we discussed the Wolf-Rayet phase during the life cycle of massive stars and the Wolf-Rayet nebula, which were present around massive stars. And then we discussed the role of massive stars in accelerating particles, and then very specific case of this isolated single star WO-102 was discussed, and how this can lead to production of galactic cosmic rays that was discussed from the modeling. So yeah, I end it here, and that's all from my side. And thank you for your attention, and I would like to have questions now.
Thank you, Prachi. That was an excellent talk. The first question we have is that do all massive stars go through a Wolf-Rayet phase in their evolutionary journey?
Okay, no. As I mentioned in one of these slides, so only the stars which are above 40 solar mass, so they go through the Wolf-Rayet phase, not all of them. So if you see here, this above 40 solar mass, so these masses which are written here, are the initial 0-age main sequence mass. So when the star steps into this main sequence, at that time, whatever was the mass is written here. So the stars which are having initially the mass which is greater than 40 solar mass, those stars eventually go to the Wolf-Rayet phase and end their life as supernova explosions.
Thank you. The next question is the formation of the shock front a result of the magnetic field of the star moving into the medium?
Magnetic field, it's not moving. Magnetic field is not moving. Actually, what I wanted to convey here is that the magnetic field is always present in the medium. But when you have a shock front, and the shock front itself is moving, because you have, let's say in case of supernova explosion, the explosion happens and the material is getting pushed outwards. So that creates shock front and which is moving. So due to this motion of the shock, the particles which are either in upstream or downstream, when they try to move, due to the motion of the shock, when they try to cross this shock front, then it experiences the head-on interaction with the this MHD waves which are present, the magnetic waves which are present there. So that is what causes it to reflect back to the downstream. So, is it understandable?
Yeah. We have one more question. So before a star enters the Wolf-Rayet phase, is it possible to predict whether it will be a WC star or WN?
Yes, so there are some evolutionary models which talk they simulate the star's evolution based on the initial mass. So will it go to WC or WN or WO? It all depends on the initial mass of the star. So let me show you one of the backup slides which I have. Okay, so can you see here? There are these three different evolutionary sequences where the stars which are having initially more than 75 solar mass, they go through WN phase and then eventually WC or WO, and then as their life is supernova 1, type 1 and C category. So whereas if you see 40 to 75 solar mass, if the initial mass is between this range, then they go through WN and WC and WO. But there, this LBV is basically the luminous blue variable phase. I won't go much into the technical details of that, but so these are kind of from the models which people have predicted. So if you have very low mass, like 25 to 40 solar mass, then it goes only to WN. It doesn't encounter this WC or WO phase in its life.
Okay, coming to our last question. Are you planning to complement your results on WR102 through further observations in X-ray and other spectral areas?
Can you repeat it?
The question was, are you planning to complement your results on WR102 through further observation in X-ray?
Yes. Yes. So yeah, it can be observed in X-rays because we see here. So this is the model spectra. So these part, if you see, this is the very high energy range. So this falls in either extreme ultraviolet or X-rays. So these in this range, if we can get some observational data points, it would be good to confirm that the spectra is how efficient it's in fitting this model. So these are radio data points. So yeah, we can observe it in X-rays to get some data points here towards the high energy end.
Thank you so much, Prachi. It was an excellent session, very enlightening. Thank you.
Thank you.
Stay having with us. Thank you for watching.